Hello everyone, welcome to the last session of 4-bit CLA adder implementation in custom compiler tool in Synopsys. So in the last three sessions, we have developed the generate circuit block, propagate circuit block, carry circuits from 1 to 4 and sum circuit. So in today's session, we will integrate them together into one module and then we'll simulate the test bench for a 4-bit CLA adder. So let's just start, right? So this is the custom compiler tool. We have created a library, 4-bit CLA adder test. And so far we have created this many cells. Now to create the final circuit, to integrate everything together, we'll create a new cell. We'll call it as ISD underscore. We'll name the cell as ISD underscore 4-bit CLA add. Okay, we'll not name it as an adder because that will be the same name as the library, right? And then we'll click on apply. So the new cell is created now. I'll click on OK. Okay, I will say ki this cell exists already. I'll call it as adder 1. Okay, fine. Actually, two cells got created, add and adder. So I'll remove one of them and I'll work on ISD 4-bit CLA add, right? Now let's move forward. Let's see if I can rename it. No, not possible. So now I have to create a view, go to new, and we'll go to schematic. And then click on OK. So your schematic screen will appear onto your screens. I'll drag a little down away from the axis. And now I'll start building up the final module as shown over here, right? All the circuits simulated together, okay, integrated together. So let's start building. So go to the instances and you have to select the library as which you have created, 4-bit CLA adder test, right? Then from here we have to select the cell. So first of all, you have to select the cell of generate block. So I will select the cell of generate block and you have to attach it into your screen. Yeah, here it is, the generate block. And I'll press the escape button. Okay, so generate block is added onto the screen. Next, I have to add, let me just push it slightly up. Yeah. So next block which I have to add is, let us see what are the options available. Propagate block. So see, remember these three blocks we have created in the last three sessions. I have to add the propagate block. I'll have to add it below it. So let's just add it over here and then we can add it below it. Okay. Yeah. So we'll add this propagate block below the generate block. I mean, yeah. So we have added this together. Now we have to add the sum block. Remember, while doing the sum block, we have done only one, but in reality, let me go over here. We have S0 to S3, right? So we'll require 4 sum blocks. So we'll go over here again. And here we'll search for the sum block. Yeah, here it is. So I have to add 4 such blocks. So I'll add it one, then second one, then third. I'll arrange it properly, don't worry. You just keep on adding it now. And the fourth one. Okay. So these are the 4 sum blocks. I can arrange them now properly. Yeah. This one also I can arrange it in line with whatever we have been doing. Okay, I am adjusting it with orientation with the first block. Here is the third one, the third sum block, which will produce S2 at the output, and the fourth one, which will produce S3. Okay, so all the blocks are added now. Now only thing left is to add the carry blocks. So I'll go over here. I have to add one by one, carry one block over here. Okay. So let me just a little bit zoom out. Yeah. So carry block, I will add it over here. Okay. Next is carry two block. So carry two block will be added next to carry one over here, somewhere around here. And next I will select carry three block. All these blocks we have created in the last session. Yeah, this is my carry three block. I've added over here. Last will be carry four block. That will be the last block and we have to work with them. So together with all these blocks will make a 4-bit CLA adder. We have to now interconnect them. Okay, so all the blocks are being added now. So now what I will do is now I will be doing full screen and then I'll be interconnecting them together one by one. First of all, let me arrange them properly. So yeah, this is proper. Next, this one. Okay, this is also proper. This I'll slightly move it down. Okay, fine. So now I have to interget. I have to delete one, I guess. Yeah, remember, if you expand it a little more, and I use this. So remember, we have built up these modules before in the last three sessions. So first we started with a generate block. So this is my generate block. And then we have the propagate block. Then comes the carry one block. These are all the modules which we have created, right? Carry two block, carry three, and finally we have carry four. Okay, carry four, this unnecessary wires have been created. We'll delete those wires, don't worry about it. Okay, let me just see to it that I will delete them. Okay, yeah. So I am deleting those wires so that it don't interfere with our design. Okay, fine. So let me delete that carefully. Yeah. So just give me a moment. I'll delete them all, the extra wires which are there. Okay, I guess we can continue further. And now we have to start interconnecting them. So let me slightly zoom and let's start with the connections. Remember, we have to assign pins also so that our final IP should look something like this. Finally, this modular design should be converted to one such IP, that is 4-bit CLE adder. And then we'll add the test bench and we test the 4-bit CLE adder together. Okay. So now let's start with the generate block. Let's complete the connections with the generate block. So over here, we will be defining a common, we'll be using the labeling technique, right? So let us start first with this. This is the wiring connection for all the inputs. Let them connect one, let us connect one by one. Okay, these wirings will be connected to the propagate block also. So care should be taken that they don't, intersect each other. Carefully you have to do. You have to take some time. Okay, systematically. Huh. Now let's connect them together. So I have to zoom out a little and I have to go slightly down. So I have to connect them with this, with the propagate block. So let me use wires again from here and let me start with first connection and connect it over here, right? So this way we have to connect it one by one. This B0 will go to B0. Then next we have A1. A1 will go to A1. And next we have B1. So this way you complete all the connections. Let us complete that quickly. Next is A2. Next we have B2, followed by A3. This is A3. And then we have finally B3. Okay. So once these connections are made, let me just save the design. Yeah. Let me save the design so that we don't lose anything. Correct. Now, after we have made this, we have made the interconnections. As you can see, we have connected, generate and propagate block will have, all the inputs, that is A0 to A3 and B0 to B3. So now let's, we can label them or directly connect the pins. So let's start connecting the pins now. Okay. We can label them also later, but let's start connecting the pin. So the first pin is of A0. So I'll connect it over here, A0 pin. Next pin is of B0. So this I'll mark it as B0 and I place it over here. Then next is again A0. I mean A1. So I'll mark it like this. Next is B1. So let me complete everything. I mean all the pins from A0 to A3 and B0 to B3. Then we'll proceed with the design. Okay, so we have added this 8 pins A0 to A3 and B0 to B3. Now next in the design is VDD and VSS. Actually VDD and VSS will be common for all of them. So what we can do is we can connect them together. So let me zoom out a little. Okay, and I'll take a wire and connect all the VDDs together. Here it is, from here to here, and okay, and from here to here. Okay, I'll connect the wire. Yeah, so all the supply voltages are connected together now. Okay. Similarly, the VDD of the lower block, that is the propagate, carry 1, carry 2, and carry 3 also have to be connected together. So that also connections I will make. Similarly, your VSS connections also have to be made together. Okay, so I'll be connecting them one by one. Here it is. The next connection will go over here. And the last one will be over here. Okay, let me delete the connection again. So this way, let me connect all the VDD and VSS together. Till then, we'll proceed with the design. Okay, all the VSS terminal, that is a ground terminal for all the blocks are connected together. The VDD terminal of all the blocks are connected together. Now we can label them. So I will add the wire name over here as VDD, and here I'll add the wire name over here as VSS. Okay. Similarly over here, I'll add the wire name as VDD, and over here I'll add the wire name as VSS. Okay. So these pins are defined now. Now I'll also define the pin over here. I'll call it as VDD, and that I will connect it over here. Okay. Similarly, I'll define one more pin, VSS. So VSS, I will connect it over here. I'll call it as VSS. So VSS will be the input pin, but acting as a supply. I'll connect them together with a wire. Okay, now all the VDD and ground are connections have been done for the entire module. Fine. So let's save the design till then. And now I have to do the interconnections between the various blocks. So let's begin. First, we'll start with the carry blocks. Okay. So right now I'll take the wire out and I will be naming it as P0. This will be, I will add a wire name later. So this will be P1. Remember to save your designs very often. So this is P1. This will be P2. And this is the wire for P3. Okay. So it's very important to label the wires because we will be using it again. So I'll label it as P0, then P1. This is a complete module, so it will take some time. You have to bear a little, you have to devote a little time to this. Then P3. Okay, so this is done. We have added all the labels for the propagate block. Similarly, we will do it for the generate block. Okay, so we'll take the wire, extend it a little bit from here to here, and then similarly for G1, G2, these are all generate terms. You'll be using it in the sum block or the carry block, one after the other. So that's why we are labeling it, so that we don't have to do it again. Interconnect them with a wire, we'll just use the label. So this is G0. This wire name will be G1. Next, this wire name will be G2. And this wire name will be G3. Okay, fine. So the wiring naming of propagate and the generate block is completed. Now we'll move on to the carry block. Okay, so we'll scroll down. We'll slightly move down over here and we'll name it as C0, G0, P0. Instead of connecting it, we'll use the labeling concept, which is very, very powerful. So let us complete it. I will complete the connections. I'll fast forward the design. Similarly, we have to do it for carry 2 block, which will be C0, G0, G1, P1, P0, and P1. Then also I will label all the other terminals, that is C1, C1 bar, then C2, C2 bar. Similarly for C3 and C4. So let me complete it and fast forward the design. You all can also complete in your own design. Okay, so in this manner, all the pins have been, we have connected the wire to all the pins of the blocks, and we have also labeled the wires. So by labeling, what it means is that suppose that this P0 has to be connected to this P0 pin. So we don't have to actually physically connect the wire. We can just label the wire. It means that these and this are connected. right? So similarly, we have labeled carry 1 block, input and output pins. Then we have labeled carry 3 and carry 4 also. Okay, so this will complete the complete interconnection for the carry blocks. Now let's go to the sum block. Sum block also, we have connected the wires to each pin, but we haven't labeled it. So let's see how to label it. It is CI bar. This is CI plus 1 bar, and this is CI. This is CI plus 1. This is GI and PI and SI. So let's see how to connect the sum block. So over here, the formula is SI is equal to GI CI plus CI plus 1 bar into PI plus SI, right? So your this S0 will be G0 C0, right? And you will have CI C1 bar P0 C0, right? So how will you label it? So this is some one, right? This is S0. So we'll label it as S0 block. Let me add the wire name. Right click. This is S0 block. S0 I mean label. This will be C0 and this will be C1 bar. Okay, we have labeled C1 bar down also. This is will be G0 and okay, I have to rename it G0 and this will be P0. Yeah. Now remember, in the final block, we should have this many pins. Let me go over here. So we have already defined A3 to A0, B3 to B0. C0 also will be input pin. So we have to define that. C4 will be output and S0 to S3 will be output, right? VDD and VSS we have already defined. So please note that we have to define one more pin over here in the form of C0. So we'll add the pin over here. We'll call it as C0. This is another input pin. So now I'll connect it with a wire. So this becomes another input pin for my IC. And S0 is my output pin, right? So I'll select the pin from here and I'll make it as output. Okay. So this is the output pin. I'll add it over here, but I have to give name over here also. So yeah, this way I will add the pin S0. Okay. Now for the second block, this will be S1. This will be S1 label as S1. So this will be C1. Now C1 is not necessarily visible in the actual IC. So C1 will label it as it is. This will be C2 bar. Okay. Because in the formula we have now Ci plus 1. Yeah, Ci plus 1. So if it is S1, that will be C2 bar. Yeah, it is C2 bar. Then we have G1. Okay. Then P1. Fine. So this way we'll complete the remaining part. So for here again we'll require output pin. So we'll have to add output pin. We'll call it as S1 and we'll connect it like this. Okay. Then this will be C2. Then we have C3 bar. Followed by G2. See, these are all generate terms, right? Let me write the label properly. This is, if you make a mistake in the label, you will not find key where is the error going wrong. So please label it properly. This is G2. Let me save the design in the meanwhile. Then finally, this will be P2. Very carefully and systematically, you have to solve this. Okay, and this will be S2. Yeah. So let me complete the remaining connections quickly so that we can proceed with the design. Okay, so in this way we have labeled the terminals and we have defined the output pins for S0, S1, S2 and S3. Now let's go back to the main block. So everything is completed, S0 to S3, A0 to A3, B0 to B3, all the pins are defined, even C0 is defined, only C4 is left. So I think we have to go to the carry circuit now. I think we have defined C0. Yes, we have defined C0. So we'll go to the carry circuit, and wherever there is C4, we have to define the output pin over here. So I'll select the output pin from here and call it as C4, and I'll add it over here. Okay, and I'll make the connections. Hopefully this is the last connection for this block, for this schematic. Okay, so yeah, we have successfully integrated all the blocks together. So let me show it to you together over here, right? This is my generate block, propagate block, all the sum blocks, 4 blocks of sum, carry 1, carry 2, carry 3, carry 4 blocks. So all are integrated together. So let's see that if it gives you any error. Yeah, we have saved the design, but let's see what are the errors which are giving. Yeah, the error is that S2 is sorted to the following nets S3. Okay, we'll see that there is an error, so we'll have to resolve it S2, this one and this one, right? So wherever there is an error, the beauty over here is that wherever there is an error, it will keep on blinking. So let me maximize that part and go over here wherever it is blinking continuously. Yeah, this is S2 and this is S3. Yeah, what mistake we did was we have defined S3 also here. So we have to redefine it. Double click over here. Let me just do it. I'll double click the label and I'll call it as S2. Hopefully this will resolve the problem. Let me see. Let's hope for the best. Yeah, finally, there are no violations in the final integration of entire circuit. Okay, so very good news is that integration of all the blocks are completed, and the modular design is giving you no problem at all. That means to say we have connected successfully all the blocks together to make it as a 4-bit CLE adder, right? Now next step is to create the symbol which will look something like this, right? So let's do that with great confidence. So we'll go to design, we'll go to new cell view, and we'll click from cell view, and the destination cell view is a symbol, and we click on OK. Yeah, hooray. So we have got the design properly, right? And we will orient it properly now. Let me slightly zoom out a little and bring that symbol away from the axis. Yeah, yeah, I have done that. I have done it away from the axis. And now let's start with it. So here I'll delete these wires. I'll orient it in such a way. I'll orient them in such a way that yeah, VSS is at the output. Let me check one more time. I'll zoom out over here. Let me check the VSS pin. VSS pin is over here. It is type input. Yeah, it is type input. No problem. So what we will do is we have the symbol right now with us. This is the final IP which we have to design. I'll design it. I'll orient it in this fashion, right? We have A3, A2, A1, A0, or else the way it is over here, A0, A1, A2, A3, B0, B1, B2, B3. In the same fashion, I'll do it. Let it be, no problem at all. And then S3, S2, S0, S1, S0. So here I'll keep it as it is, and C4 will be output, right? So let me orient it. First of all, we have to delete all these things. Then I'll quickly orient it properly. your VSS and supply everything proper. So in the meanwhile, let me complete this. Yeah. Inside names also we have to chop it out. Okay, fine. And now let me orient it. Let me, I mean, so that we can proceed with the design. Everyone has understood now what we need to do. We have to arrange the pins in such a manner that it looks like this. And we'll name it as it is, ISD 4-bit CLA adder. We'll name the final, IP as this only, right? So yeah, so let's start now. I will proceed with the video. You can do it in the meanwhile on your own. Okay, so all the pins are oriented properly as per the design, right? C0, A0, A1, A2, A3, B0, B1, B2, B3, right? This is C4, S0, S1, S2, S3, and VDD and VSS. Now, also we have to rename this. Let me take it a little that side. Yeah, outside. And I'll rename this IP as ISD underscore 4 underscore 4-bit. Let me see what was the IP. 4-bit CLA adder. So CLA add. So I'll name it as 4-bit CLA add so that it fits over there. Okay. So let me add it in the center. Yeah. So this becomes my IP. This is what what we were supposed to build over here, like this, right? And exactly in the same manner it is. It's looking exactly in the same manner. A very happy moment. Now we can save this, right? So once it is saved, let me click on save again. Yeah. Once it is saved, you can close this, and you can also close the schematic which we have built over here. I mean the final integrated circuit. And now we have to create a test bench. So I'll right click on new test bench for the final one. So here in the main block, I'll add TB. So this will become as my test bench. The same name I have to give over here. ISD 4-bit CLA add test bench. Okay, so I'll click on OK. And here, this test bench, I will be creating a view. This will be new. And I'll select it as schematic. And then I'll click on OK. So lastly, new schematic, the final schematic will come. And here we will test whether our final, IP, which is showing over here, it's working or no as a 4-bit adder or no. So let's begin with the analysis. So over here, once we select the, I am moving away from the axis. Yeah. So once we have created the test bench, you have to go to the instances and select the library. So your main library will be 4-bit CLA adder test. And from here, we will add that the main block which we have created over here, right? The symbol. So here I will add it. So yeah, this symbol has been added now. And now next what we need to do is we need to add various pulses, inputs, VDD, and also we have to connect at the output if we want to connect the capacitive load, right? And let's start building it. So before doing that, what we will do is I will be opening this one simultaneously. There are some input pulses definitions which we have to take care. So these are the input pulses definitions. According to this only we will be designing, right? So let me keep it open as it is over here, right? Hope it is visible. Yeah. And let me just fill it the entire screen like this. I hope nothing is, everything is comfortable. Yeah. So now let me go to full screen mode. so that you have a better view of things over here. And actually, in reality, the other view was better for the simple reason that we have to connect the inputs over here, right? So I have to slightly move my screen that side. Okay, fine. So let me start for the final test bench. So, okay, I will slightly keep it over here. Let me orient it properly. And now let's start. Okay, so you have to go to the instances, and now you have to select the library analog lib, because the V pulses and VDC are over there. And then from here, I will type VDC. I'll select the VDC. Remember, we are going for a 28 nanometer PDK, so we can go as low as below 2 volt also. So we are giving here 1.05 volt. So when you click on OK, your VDC comes over here. I mean, let me paste it like this. Let me keep it like this over here. Okay. Yeah. So I've added the block. Now let me do one thing. Let me just add the labeling part also, so that it becomes easier. It will become very easy for us when we connect them together. Let me add quickly the labeling part. So I will slightly fast forward it. Let me show you to how to do it. So I'll right click, add the wire name, and I call it as C0. Okay. Similarly, let's do it without fast forwarding the video. So this is A0. Let me add the wire to A2. Then this is concept is called as labeling. It's very powerful when you're doing in simulating any circuit, so that it saves a lot of time, and it keeps the design neat and clean. No overlapping of wires will disturb you by this labeling concept. So labeling concept and modular design concept has made this CLA adder very, very simple. Okay, fine. Similarly, I have to label the output also, because for simulation labeling is required and mandatory. So here I will quickly label the outputs also, output pins. So there are 5 output pins. C4, which is the carry out bit, S0, S1, S2, and S3. Fine. So I've added quickly the wires. Now I'll label them quickly. This wire name will be A1. Next will be A2. Next will be A3. Then we have B1. I mean B0. Then we have over here B1, B2, and B3. Similarly, at the output C4, I'll name it as C4. This will be S0. Then we have S1, S2. Okay, S2. Label them properly. You won't want to make a mistake over here at the final step. Yeah. So labeling is completed. Similarly, at the I'll scroll a little down so that I can label the VDD also. So I'll just connect a wire from here to here, and I label this node as VDD. Okay, fine. And also I have to label them also, these things. I will do that later, and I can add the ground later. But now let's concentrate on the design, adding the input pulses. So yeah, So one input pulse I have added, one DC supply I have added already. Let me adjust it over here. Yeah, this is proper. Okay, oops. It is going down again. Yeah, why it keeps running down? Okay, hopefully this will suffice. Yeah, now I'll go to the pulse, go to the add instances. From here, I will type V pulse. I delete the previous one, V pulse. Okay. So for this V pulse, I have defined the parameters over here, which are given. So the first parameter is DC voltage will be 0 for all. Voltage 1 is 0. The first one is defined for C0, right? And it is a C0 only. So here we have been writing over here 1.05 volt. So voltage V2 will be 1.05. Then the delay time is 4.5 nanoseconds. Okay. Rise time is 0.1 nanosecond. Fall time is also 0.1 nanosecond. Pulse width is 4 nanoseconds and the period is 8 nanoseconds. Then I can keep this, which is moving over here, steady onto the screen. Okay. This I'll move on that side. So can add all the various pulses. Okay. So this will become my C0. I can add the label over here like this. I can add the ground also. Ground I will add at the end. So this I will call it as C0. So this is my C0, right? So this was the definition which I was referring, right? If it is not so clear, I will just zoom out a little. Yeah, this is C0. Next we'll go for A0. Again, I'll select the pulse. And over here for A0, we'll have again the voltage for all of them is 1.05. Delay time is 2 nanoseconds. Rise time is 0.1 nanoseconds. Fall time is also 0.1 nanoseconds. What is pulse width? Pulse width is 5 nanoseconds over here. Let me define it as 5. It is not properly defined. Pulse width is 5 nanoseconds. Okay. And then I can, paste it over here. 1.05, 2 nanoseconds. Let me confirm. Yeah, it is proper. So this is my A0. So A0 I will add over here. Okay. A0 I will slightly push it a little. Yeah, this is my A0. I can add a wire so that I can define a label. Yeah, so wire has been added. And now I'll right click, add the wire name as A0. Fine. Next is similarly, I will add all others and I will be defining it as A1, A2, A3, B0, B0, B1, B2, B3. So similarly, I'll define all the other pulses in the same manner and I'll keep the design ready so that we can proceed with it. Okay, so we have labeled all the pins. Let me maximize the screen now. Yeah, we have labeled all the pins. Now it's time to add the ground. So from here, we'll go to cell and type GND, ground. Yeah. So we'll add the ground one by one. I think we have to push this all the sources a little down. So wait a minute, I'll do that quickly. I'll use the move button to slightly, okay, sorry for that. Okay. Okay, I will use the move button and push all the sources slightly. I'll still push the above sources slightly up so that we have enough space for the ground. Yeah. So let me show it to you. Yeah, it's proper now. And now we'll add the ground one by one. So one ground will be required over here, another over here, another over here, another over here, right? and below also will require the ground. So let me minimize slightly. We're requiring ground over here as well. So I've added all the grounds. Just a placement is required. Slightly you can place it properly. Yeah. So I've added all the grounds. Now it's just a placement issue. So this ground will go below over here. Okay, let me just. Okay, I guess I have to add it like this. Yeah, this will go below over here. Similarly, I have to add all of them and then connect them with a wire. Yeah, it will take 2 minutes, but it's worth the wait. We are almost completing with our design, which we were doing since last 3 sessions. More than 2 hours, 3 hours of work. So if it works, nothing like it. So we have used the modular design approach and we have used the powerful labeling technique in this design, right? And now I'll quickly connect the grounds together and we are ready to simulate a circuit. Okay. So let me connect all the grounds. Okay, so all the ground connections are also made, right? Let me just make a full screen attempt. Yeah. So all the ground connections are completed and we have applied a pulses for C0, A0 to A3, B0 to B3. VDD is applied with 1.05 volt. Ground is connected properly and we have defined labeled the output node. Now we'll save this design. We'll save this design and we'll run for, yeah, there are 7 warnings. Let me see which are the warnings over here. Yeah, all the 5 warnings are related to output because they are floating. That is fine. So over here, what is the problem? Let us check it out. Let me maximize a bit slightly. Okay, the ground is not connected or what? Let me see what is the problem. Yeah. Okay, fine. So let me delete that ground. Okay, what I will do is I'll delete this ground and I'll connect it to some other pin. Yeah, so I'll be connecting it over here. That is absolutely fine. It's one and the same thing. Yeah, like this. I think this will work. Let's see now. Let's run it. There should be only 5 warnings showing that all the output nodes are floating. Yeah, 5 warnings are there. So we are ready to go. To avoid these warnings, what we can do is we can add a capacitive load over here, but it's not necessary, not needed. Now we are ready to simulate a circuit. So what we will do is we have to create a test bench now. I mean, we have created a test bench. We have to go to tools, go to prime wave. So we'll do the test bench simulation. Here in the model file, we will add the model part. So part you will get it from, let me just go to Windows and move out of the full screen. So here we'll go to library manager. In my case, it is located over here. I'll copy the part from here. I'll again go to the test bench and double click over here. I'll add the part like this. Yeah. And then the model file will be stored inside that part. So I'll go, it's stored in the HSpice folder. In my case, yeah, this is the library which we have to add, right? Then section, we have to select it as TT. Okay. Then press on OK. Then for the analysis part, we have to select transient response. Time step, you can give it as around 0.1 nanoseconds. And the time period will be around 6 nanoseconds. And click on OK. Now we have to go to expressions, output expressions. We have to add one by one. So first we'll add C0. Okay, click over here. It will take some time for the first time. So the first one we will add is C0. Just a minute. Okay, after selecting the analysis, we have to click on the expression and click over here. It will pick up the parameter from the design. So first we want to plot C0. Okay. Similarly, one by one, you have to pick it from here. Sorry for that. Next parameter will be A3. Next variable we have to add is A3. So we'll select A3. Automatically it will assign the color. Similarly, A2. Now next is A2. Okay. Next parameter will be A1. So we have selected A1. It's automatically assigning colors. Then we have A0. Then we have B3. B2 next. It will pick up B2 from the label. Next is B1. This is B1. Next will be B0. Now will come S3. Next will be S3. There is some tree. Next will be S2. So these are all the variables which we have to plot. Okay. It's a 4-bit CLA adder. So it will have two 4-bit binary digits, binary numbers. Next will be, it will have a 4-bit sum from S3 to S0. I mean S0 to S3. And it will have one carry in the form of C4, which is called as a C out carry. Okay, I guess all the variables have been added now. Now I will go to simulate and click on netlist and run. And let's hope that your simulation comes correctly. So it will take 5 to 10 seconds for the first time if you click on simulate netlist and run. Yeah, the very soon your input output waveforms will appear onto the screen. Yeah, let's pray that it works. It will work definitely, confidently, but let's hope for the best. See, all these waveforms are together. We have to ungroup them. So I'll right click over here, click on ungroup, right? And then I'll turn off this grid. Yeah. So now we will view these waveforms. It is mostly seems correctly. I mean, according to me, it is correct, and it's a good news. And we will check the functionality of this adder very shortly now. So let us start. Okay. So I have already done the functionality. I suppose that it will work here only. So let me see where I have done it on the PDF. Yeah. So this is the inspection from the input output waveforms from 0 to 1 nanosecond. We have A2 as 1, A2. So let me also show you all one more thing. Okay, just wait a second. Okay, I've opened a document wherein I'm explaining the 4-bit binary addition process. So let's say we have A0 to A3 as 1-bit 4-bit binary number and B0 to B3 as another 4-bit binary number, and we have to add them together. So the sum will be S0 to S3 and the carry will generated will be C4, which is the C out carry. C0 is the initial carry, and intermediately C1, C2, C3 also will be generated, which are intermediate stage carry, right? A0 to A3 is a 4-bit binary input A. B0 to B3 is a 4-bit binary input B. S0 to S3 is a 4-bit binary output. C0 is the 1-bit carry in bit, and C4 is the 1-bit carry out bit. So we have written in this sequence only over here in the example which we have explained. So this is A0, A1, A2, A3, B0, B1, B2, B3, S0, S1, S2, S3. This is C4 and this is C0. Okay. So in the first case, I cannot expand it a little more than that. So yeah, in the first case we have C0 is 0, right? Then A3 is, let's read it from here. This is A3 0, 0, 1, 0. So it is 0, 0, 1, 0. And B0 to B3 is all zeros only over here, as you can see very clearly. And over here, output will be some S0, S1, S2. S2 will be 1. Yeah, S2 is 1. And S0, S1, S2, S3. So 0, 0, 1, 0. You'll get, and carry 4 is 0. Okay. Carry 4 bit is 0. Fine. Now let's check the next case. Next case, from 1 to 2 nanoseconds, everything is 0. Yeah, as you can see, all the pulses are low. So output will be 0, 0, 0. So that is there. That is correct. Now from 2 nanoseconds, 2 nanoseconds to 2.2 nanoseconds, what is happening? Your A0 bit is becoming 1. A0, I mean, sorry, this is, yeah, 2.2 nanoseconds to 2.2 nanoseconds, your A0 bit is becoming 1. Yeah. So A0 is 1. Rest all are again 0 only. This is 2.2, I guess. So rest all are still 0 only. Right? Here it is. This is 2.2. So rest all are 0. So what will happen to the output? Output may we will have S0 as 1. S0 will be 1. S1 will be 0. S2 will be 0. S3 will be 0. And C4 also will be 0. So you will have at the output 1, 0, 0, 0. So here it is correct. Now from 2.2 nanoseconds to 3 nanoseconds over here, right? What do we have? We have A0 as 1, rest all A1, A2, A3 is 0, C0 is also 0. Then B2 is becoming 1. Here it is B0, B1, B2, B3. So B2 is becoming 1. Now let's check the sum. So at the sum side, we have S0 as 1, S0 is 1. Then we have S1 as 0, S2 as 1, and S3 as 0. So you'll have 1, 0, 1, 0. So it is correct. Here C0 is 0 and C4 is also 0. So this third instance is also correct. We are moving in positively in the right direction. Then let's check it whenever your carry is 1. Now let's go to the case where carry is 1. Yeah, carry is 1 from 4.5 nanoseconds to 4.8 nanoseconds. So somewhere around over here, carry becomes 1. Okay. So now A3 is 1, A2 is 0, A1 is 1, A0 is 0. So we have 1, 0, 1. I mean 1, 1, 0, 1. And carry is also 1. C0 is also 1. What about B0? So B0 is 1. I mean, this is B0 is 1. Then we have B1 as 0, B2 as 1, and B3 as 1. So we have 1, 0, 1, 1, right? If we add it over here, this will be 1, 1, 1, 1 and carry 1. 1 and 1 carry, I mean, sum will be 0, carry 1. 1 and 1, sum will be 0, carry 1. And here the extra carry will be generated, output C4 will be 1, right? So let's test it out. Actually, it should be 1, 0, 0, 1, right? So let us check it out. S0 is 1, that's good. S1 is 0, S2 is 0, S3 is 1. So 1, 0, 1, 1. Let's see if a carry is generated or no. Yes, carry is generated, carry C4 is also 1. So this is also verified. Now let's check it one more last case from 4.8 nanoseconds to 5 nanoseconds, right? So from 4.8 to 5 nanoseconds, your carry is 1, C0 is 1. Then we have A3 as 1, A2 as 0, so 1, 0. Then A1 and A0 are 1, 1. Yeah. And from B0 to B3, all are 1. As you can see, this is B0, 1, B2 is 1, B1 is 1, and B3 is also 1, right? So all are 1, 1, 1. Expected output is sum should be 1, 1, 0, 1. and carry should be 1. Let us check it out over here. So yeah, S0 is 1, S1 is also 1, S2 is 0, and S3 is 1. Yeah. And what about the carry? The carry is also 1. Yeah. So the waveforms are perfectly working as a as a 4-bit adder. All the instances, most of the instances are correct. So the input output waveforms which you see in front of your screen is validating the functionality of, let the screen appear. Yeah, sorry for that. Yeah, this waveforms, input output waveforms, that is it's showing the addition of a two 4-bit numbers, input carry and C4 carry. So it's perfectly all right. Absolutely no problem. And the wonderful news is that the waveforms are going as low as amplitude as 1.05. And we have a period of around, 10 nanoseconds. So that is around zero point 0.1 gigahertz. So your circuit is working with very low voltages, 1.05 volt, and it's working at a frequency of around clock frequency of around 1.1 gigahertz. So it's absolutely correct. So a very happy moment over here. We are getting the output perfectly all right. Now, if you want to check the netlist, we can do that. So to check the netlist, you have to go to the simulation. You have to go to netlist and click on display. Okay, so this is the netlist created. As you can see, the main library file name 4-bit CLA adder test. Then the results and name, test bench we have created 4-bit CLA add test bench. As you can see, all the intermediate sub-blocks, sub-circuits are created. Sub-circuit is the modules which we have, which we have identified, modular design. So these are all sub-circuits, some circuit, carry 1, carry 2, propagate and generate. So that is what it has been shown over here, all the sub-circuits. See, this is the OR gate, then we will have propagate block, then we have sum block, okay? Then we have carry 1, carry 2. Fine, so this is your netlist. You can check it out for your design, right? Let me close it. Yeah, so our result is successful. Let me close this test bench, and I will be saving it so that I can next time if I want to view, I don't have to do it again. Yeah, so wonderful news. This 4-bit CLA adder, which is our IP, which we have designed it over here. We have applied the test inputs, I mean the pulses to all the pins, from A0 to A3 and B0 to B3, right? Along with C1, C0 carry in bit, and we are getting perfectly a perfect addition of 2-bit, of 4-bit addition of binary numbers, right? One thing if you notice is that the result will work if the decimal is more than 15, okay, right? If the binary equivalent is more than 15, then a carry will be generated automatically, right? So that is the other advantage. And other advantage of this design was if I double click over here, see this block will come, right? So this is the block which we have built and which we are so proud of, the modular block design. Okay, so in this block we have generate, propagate, all the sum blocks, all the carry blocks, all working together to give you one single IP. Fine. And what is that IP? This is that. This is the schematic of it, right? And that's the symbol. So this is what we were working for since last 4 sessions, right? And that is the design what we have created, and that is what it looks like over here, right? So we were successful in designing the modular 4-bit CLA adder with a modular design. Here it is. Okay, very satisfying result. The there is no problem with 4-bit CLA adder addition at all. Everything is working perfectly well. And finally, I want to show you all end this session by showing you all the IP which we have initially proposed and we initially achieved. Okay, so very good results. I want to acknowledge, IIT Hyderabad Hackathon, which provided us this tool, right? Synopsys tool. It was a cloud-based analog IC hackathon, which we have been using it. And today is the last day of the hackathon, 1st March, and I have showed the complete working of my design. Now, I have also written a report of it. We were supposed to write a GitHub report. So here is the report. Y'all can check it out later, right? I will provide you in the comment section. So here every detail how we have started, each and every step is explained in detail what we have experienced in the last 4 sessions. You all can have a look at it. Each and every step is explained clearly. You all can also implement it at your own pace. Let me show you something. Yeah, this is the 4-bit CLA adder schematic, which we were so proud of. Let me show it to you. Yeah, this one. And then further we have this IP design, right? Test bench created, the input pulse definitions, the supply voltage definitions, the test bench, and the final output. Yeah, here it is. So that is what we have achieved right now. And also the verification of the binary addition. 4-bit binary addition is also explained, and the conclusion, right? So I want to acknowledge cloud-based analog IC design hackathon, Synopsys India, Kunal Ghosh, the founder of VSD Corporation Private Limited, Professor Chinmay Pandya from IIT Hyderabad, and Mr. Samir, Durgoji from NIT Karnataka. Okay, so my name is Inderjeet Singh Danjal, Assistant Professor, KJ Somaya College of Engineering, Mumbai. Right. So yeah, we conclude this session now. We have simulated the entire 4-bit CLA adder in the 4 sessions, and now it's time to say goodbye. So thank you all for listening to the session. So these are all the cells we have created and we have reused, and we have achieved a 4-bit carry look ahead adder successfully working with the modular approach, right? And finally, we created this IP, I mean, symbol in the form of IP. Yeah. So that's it from our side. So yeah, thank you everyone.